Okay. So in case of supervised learning, it is very simple that I need certain labels to identify something. For example, if you are studying something, okay. For example, you are studying a chapter of maths. So first, you will try to learn from the examples. Only then shall you opt for the back questions or the exercise questions. Or rather, in the class, your teacher teaches you how to do certain problems, and then you appear for an examination. Right. So when this initial training is guided by someone, supervised by someone, it is called a supervised learning method. Okay, cool. Now, what is unsupervised learning? So basically, in this case, we try to capture the intrinsic property of the data. For example, you from your college, there's a picnic. So you all go in the same bus and then eventually are dropped in the picnic spot. By default, you will see that the computer science department has formed a group, the statistics department has formed a group, the mathematics department has formed another group, and so on. Why is this? You all know your fellow students from your department in a better manner compared to some other students of some other department, right? So by default, you guys share some same property. So you tend to group together. This is an example of unsupervised learning. So is it clear till now? Would I please unsupervised learning? Okay, yes. For example, you have a bus taking all the students. Your college has organized a picnic. Okay. So you all eventually go to the picnic spot. But after reaching the picnic spot, you will see that several groups are being formed. Okay. For example, the students of the maths department will form a group. English department will form another group. Computer science department will form another group. Okay. But no one is forcing this. This is happening automatically. And why is this so? Why is this so? Because you guys know each other well, and this is why you tend to group together. So I can say that you guys share some property such that you club along together. It's like birds of the same feather flock together. Okay. So this is what unsupervised learning means. That basically the data has a property of its own and similar related features tend to group together. So this means that labeling happens on its own. There is no labeling needed. It's just similar features will club together. Features having similar properties will club together. Okay. It's just like birds of the same feather will flock together. Where will we get our projects? We'll get your projects later. Don't worry. Yes, this is a form of clustering. Exactly. So now we come to reinforcement learning, where there is a concept of award or reward. Okay. So for example, you are solving a problem and your teacher says, okay, this is where you are going wrong. Stop at this point. So you will discard that technique and from your previously knowledge of what you have learned about this problem, how to solve this problem, you will try the same thing in some other method. Okay, this is called reinforcement learning. Cool. Is there any doubt? Anybody is there in doubt? Please mention it. Okay, so should I proceed? Voice is not clear. Okay, now is it clear? Hello. Yes. Okay. So let's proceed into our topic today, that is regression analysis. Okay. So why we are using this? So basically, this is the first machine learning model or first machine learning algorithm that we study about. That being one. Secondly, this is forms the basic for us to learn how to establish relationship between variables. Okay. And we try to derive the information of another variable from a previously known variable or from other variables. Okay, so basically we are using one variable and we try to derive information about others and so on. So as the term suggests, regress means to move back. Thus we need to back calculate to find the relationship between variables. Okay. So next we need to learn about independent variables. So what do we mean by independent variables? The variables which are required to predict another variable is known as independent variables. That is the input variables which are independent of some other variables, and these can be used to find the value of some other variable. And what is that other variable? That being my dependent variable. So these are the predicted values, okay, that are a response to certain uh, independent variables. Okay. For example, you can say that the area of a flat that predicts the house prices. So this area, this is independent, but the house price will depend on these independent variables, that is on this area of houses. Okay. So next is we have some applications where we try why is this used to predict a variable on one or more variables, okay, or measure the influence of one or more variables on another variable. Okay, so far so good. Are we clear about this? Okay. So next we learn about simple linear regression. So we consider several. Before that, let's just know something known as the best fit line. Just focus on this graph. Okay, just focus on this graph. So we have multiple data points like this. I have a beautiful line that covers almost all the points. But what if I had a line like this? Please follow the cursor. I had a line like this parallel to the y-axis. So would that relatively cover all these points? Hmm? Would that relatively cover all these points? No. Okay. Right, exactly. So suppose I draw a random line like that. How do I fit it into my desired line? So if I draw a perpendicular from this point to my line, okay, for now consider that I have drawn this as my randomly drawn line and we need to rotate it or something to find the best fit line. Suppose this is not my optimal line and I need to find it. So I try to calculate the distance from these points to this line. Okay, so we need to drop a sorry. So we need to drop a perpendicular from the point to the line. It has to be like least square of distance from the most number of points. Exactly, exactly. So we drop a line and we calculate the values, that is the distance from it. Okay. And we take, and how do we calculate this? Say y, and this is y cap. Okay. So we square each distance. Okay. Say that being y for now. Okay. Or y cap. Okay, let's consider it to be y cap. So I'm dropping perpendiculars from this. This is called my residual value as well. Okay. So when I am drawing these lines, I acquire a y value, so and I repeat it for all these points. Okay. So I need to draw a line through the data. Then and I measure the distance from the line to the data and square each distance and add them up. Okay. Then I rotate the line. Cool. With the new line, I measure the residual squares again. And then I sum up the squares. Then I need to rotate it again. And similarly, in this technique, I try to find a rotation that will produce the minimum amount of least of the square values. Okay, that is the least square of distance. Cool. Is everything clear till now? What is residual square? Okay, so residual square is this. I said that what is residual? Okay, so when you drop a perpendicular from this point to the line, this distance, this is called the residual distance. Okay, or the residual. That is the distance from a line to a data point. Cool. And when you square these residuals, you get the residual square. Okay. Okay. So far so good, I guess. Perpendicular distance is the residual distance. Yes, exactly. When you draw for linear regression, the lines are always perpendicular. It's not like this. Okay. Not like this. You draw a perpendicular from this point to the line. Clear? Yeah. So now we rotate the line and we calculate the values to find a line that has the least values. Okay, that has the least squares. Okay, least square value. Clear? So this is how we can fit a straight line. Next, what we do is, so this is the equation of the line y is equal to mx plus b or mx plus c, where m is my slope and b is my intercept. So what is intercept? Anybody? It is the value for y when x equals to 0. Okay, that is the where the y value will start if my x is 0. And what is slope? It determines the rate of change or the change in the direction, right? Slope for rate of change, correct. That is the rate of change of y for a change in x, for a unit change in x. M is the slope here in the first example, tan theta. Cool. Okay. So eventually we are trying to obtain a y that will have an equation like beta 0 plus beta 1x plus error. This is my error term. Okay. And we have the intercept beta 0 and the slope as beta 1x. This is for one variable. Okay. That is for a simple linear regression. Cool. Now we saw the concept of fitting a best fit line, right? We can do linear regression from this concept itself. How? Once we have obtained the best fit line, once we have obtained the best fit line, what we need to do is we to predict some future value, we need to obtain the nearest estimate of m and b, that is of my slope and the intercept, so that once we find the optimum m and the optimum b, we just need to place the value of the newly arrived x, and then we can calculate the predicted y, right? So far so good. Have you understood simple linear regression? Clear? Crystal clear? Oh, ah. So next we move to multiple linear regression. So in this case, I previously I had only one independent variable, that is x. But now I have several independent variables, x1, x2, and thus we need to calculate, or we need to find the best estimate of these independent variables. And how is this done? We need to find the slope for each and the overall intercept. So the equation comes out to be y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 and so on till the nth term and the epsilon, which means my error term, right? Cool. Please repeat the fitting part. By fitting part, you mean the line of best fit. How to quantify epsilon? See, epsilon, that is what we will calculate in linear regression. Wait, we are not completely done yet. We need to minimize this error to find the best fit line for the linear regression. Hmm. So let me explain the line of best fit once again. We randomly draw a line between the data points. Okay. Now, this line might be erroneous. That is, this might not cover all the points. To how to ensure that it covers all the points, I calculate the distance of all these points from the line and I take their squares, right? And then I rotate the line so that I finally arrive to a line that has the least distance from each point, the least square distance from each point. This is my least square method of finding the optimum lines. Okay, of finding the optimum best fit line. So clear? Rotate at what angle? 180 degree. Right, whatever angle you want. Just keep rotating. Obviously, would do a massive change. We try to do it in small angles. Okay, cool. So next, we try to do logistic regression. This is basically a classification. Although the term suggests regression, this is basically a binary classifier. So, in what is the difference between regression and classification? In case of regression, we try to predict a value, but in case of classification, we try to predict whether the data points belong to certain classes or not. Okay. For example, I have cats and dogs. So my values will just place the data point into whether it belongs to class cat or whether it belongs to class dog. Okay. So what is logistic regression all about? So in this case, since it is a binary classification, okay, in case of classification, I try to separate the data points between two classes. Okay, hence the term classification. Clear? Again, okay, let me repeat. So in case of classification, what we do is that we try to say whether a data points belong to certain class or not. What is class? Basically my labels. Okay, so if I have several images and I want to classify, and each of them belongs to a cat or a dog. So basically I have two classes, a cat class and a dog class. Okay, so if I try to distinguish a data point into class cat or into some class dog, then it becomes classification. But what is done in case of regression? If I have a data point and I am trying to predict a value to inference it, for example, as I had mentioned, that if I have the square area term, that is the square area foot, area per square, the square feet, the area of a house in terms of square feet, and I try to predict the house prices from this value, from the square feet value, then this is an example of regression. Cool, cool. Which part? Okay, for the regression part. Okay, so classification you understood. For regression, suppose I want to predict some quantity. For example, if I have the area of a house, okay, in terms of square feet, then I want to predict what is the price of that house. Okay, this is an example of regression. Basically, or you can say, if I have the mouse weight, what would be the size of that mouse? Okay, cool. But hello. So basically, regression is used to estimate a value, whereas classification is used to assign a label. Okay? So how? In case of regression, if we provide the model input features, then the model learns a relationship between the data and predicts a continuous output, like the house price. Okay. But in case of classification, the model data will learn the input features and map them to some discrete label. Okay. For example, if it is a credit card fraud or non-fraud. Okay. Understood? Clear? Yep. So next we look into this logistic regression. So this is a binary classifier. Okay. So I try to predict within 0 and 1. So there are points like this, the green dots, and I obviously cannot cover these points through a straight line, right? But this can be covered if I have an S curve like this. Okay. So And what about if my points belong here? I need a probabilistic value such that if it is less than 0.5, it shall be mapped to 0. And if I have a value greater than 5, it shall be mapped to 1. Right? This is done through the sigmoid function. It predicts whether yes or no or true or false. Only two categories. Exactly. Exactly. So basically, if I had a linear transformation y is equal to mx plus c, let this w transpose. Okay. So ignore this. Consider it to be m and c b being the intercept itself. Z is your y here basically. Okay. So suppose this is of equation. This equation is of form y is equal to mx plus c. Oh, sorry. Yeah. Suppose this equation is of form y is equal to mx plus c. Then if I use a sigmoid function over it, I will receive a value that is 1 or 0. Okay. So to do this, we need a probabilistic value, and this is how it's done. Okay. So since it is a categorical data, I need a probability that will say to which class it belongs. To do this, we have the sigmoid function. Cool. Everybody clear about it? Anybody, any doubts? Okay, please repeat. Sure. So, what is sigmoid function? A sigmoid function is of type 1 by 1 plus e to the power minus x, sigmoid of x. So, this is basically my sigmoid function, which is an S-shaped curve, and this is used to map a value to 0 or 1. Okay. For example, if you had points like this, sigmoid helps in deciding the category again. Exactly. It helps in deciding the category. Okay. So for example, if I have these data points, one on 0, x is equal to 0, and the others on, say, y is equal to 1. Okay. So can I cover these through a straight line? No, right? So to cover this, I have the sigmoid function, and is a shaped curve that will cover these points. Okay. Now, to get this done, I might receive values. Since it is a probabilistic approach, I might receive values that are between 0 to 5, 0 to 0.5, and 0.5 to 1. So, the values that are lesser than 0.5, I map them to 0, and the values that are greater than 0.5, I map them to 1. Clear? Okay. So this is how it's done. This p being my predicted values y. Okay. So these y is equal to a sigmoid of mx plus c, and you have it in this form. So I couldn't find just one representation. Yes, the equation, this is the equation. Follow this. Follow this example. So this was my curve, the linear regression example. This is my equation for it. And if I need for logistic equation, I'll just apply a sigmoid function on z. So basically y cap becomes sigma of x mx plus c. Okay. So essentially I will have p is equal to e to the power mx plus c by 1 plus e to the power mx plus c. Cool. Can you please repeat the linear transformation line from earlier? Which part? What is W power T? That is not T power T. That is basically a transpose. This is why I've asked you to ignore that. So tomorrow when we'll talk about matrices, or we can talk about it today itself. So in case of that, you need to calculate the transpose of the weight matrix, or here in case the slope matrix. Okay. So that is the transpose thing. When you know the transpose of a matrix, row becomes column, columns becomes row. Okay. Transpose. And when we were talking about sigmoid function first, okay. Okay. In case of sigmoid function, I couldn't have drawn a straight line to cover all these points. So that I can cover all these points, I use the sigmoid function. Okay. So basically, if I have a value between say 0.5 to 0, then that is mapped to 0. If I have a value from 0.8, from 0.5 to 0 to 1, then the mapped value goes to 1. Clear, Shoradipta? Oh, now, then first let's gather of what we had learned about linear regression, the steps. Okay. So I was drawing a line randomly through the data. Okay. Then what was I doing? I was rotating the lines to find the best fit line. Okay. Now, how is this done? Here comes the concept of cost function. Okay. So the line that has the best fit is considered to be the optimal line. Okay. Cool. The line that has the least error is called the best fit line. How is this calculated? Okay. This is done, but we were rotating the lines, right? We were rotating the lines to find the line that has the least square. Okay, to receive the optimal best fit line. How do we emulate that through a formula? This is what the cost function means. Okay, let's say I need to minimize the distance difference. Okay, just like say if I predict something and I have the original value of it, I will see to it that the difference between them is minimum. Correct? Correct? So hence I was calculating this yi prep. Sorry, this yi prep, and I was given this yi, this being my labels. This is the original value, and this is my predicted y value. Right? So I am doing this for each sum, for each data point. Right? So I was doing this for each data point. Then initially I get this. Now to add them all, to add all of them for least squares, right? So to add all of them, I use the summation technique. And then to find the average value, I am using by n. So often it's advised that you take 1 by 2n, because next we learn something known as gradient descent that involves the partial derivative. So this 2 and that 2 gets cancelled out. Okay. So far so good. Did we understand what is cost function? Why need a cost function? Why is the replace done? Which replace? which
1 by 2 n. 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 1 by 2 n
Oh, yi period wala. Okay, okay. Because you're just putting in the formula for yi. So how are you calculating the yi period? Through m and c, right? Y is equal to mx plus c. So that is what is happening here. Okay. Yeah. So does anyone else have any doubt regarding cost function? Which one? The cost function. Okay. So basically, and if we think about the line of best fit, we were rotating the lines and then we were trying to find the line that has the least square error. That will be my line of best fit. So how do we find that best fit line? We need to look for some value which is minimum. Okay. So how to put a quantity to it, right? So we put a quantity to it using a cost function or objective function. That is, I want to minimize the distance between the data points and the line to some values, then measure m and c. Now this is done through the cost function. Okay, clear? Why are we squaring the difference? Because there might be a negative value. Okay, so if I don't square it, it can be yi minus y prime that can lead to a negative value, right? So to overcome this, we are squaring it so that all the numbers are always positive. Okay, so now let's look to constructing this cost function. Okay, so how do we do this? You are already given the original values and you're calculating the and then you're calculating the predicted values. Okay, through y is equal to mx plus c. Okay, so once you're calculating these predicted values, you take the difference for it. Okay, so you get for now you get this cost function as yi minus y prime. Okay, then you're trying to minimize this value. Okay, now before that you get yi minus yi prime. Now you want to keep this positive. Okay, because if it goes into one say negative entire negative term, you don't know whether it will be some erroneous term or the calculation will be perfect, so we try to keep it in the positive section. So I just calculate yi minus y prime whole square to avoid the negative terms. Okay, now this is for one term. I need to sum along all these points. Okay, I need to sum along all these points. So this is why I use the summation. And then to restrict my term to a lower value, I use the average. Okay, you can take modulus as well. There's a application for it using modulus, but generally this is advised. Cool. And coming to why are we not square rooting it? Okay, so we are not square rooting it because this is a term quantity in itself. Okay, this is a separate quantity. Now, this is why it is called least square error. Okay, for now, since we are taking the mean, it is the mean square error. You can also take the root, then that becomes the root mean square error. Okay, got it, Pearl? Here, can we use n instead of n? You can use 2n. Yeah, obviously. Actually, it is preferred to use 2n. Okay, why is this so? I'll explain in the next part. But before that, just give me a thumbs up if you have understood this. I need to know that you all have understood this properly. Only then can we proceed. you like my channel, don't forget to subscribe. Subscribe. Okay. Subscribe to guys, please like and subscribe. Okay. So it seems like we have understood this. Now we were looking for a term. We were looking for the line. Again, let's think about with respect to the line. So we were rotating the line to find a minimum value or minimum erroneous value, right? So that means we need to minimize this error, right? So basically, the value we obtain from this cost function needs to be minimized. Okay, that should have the minimum value to find the best fit result. Correct? Clear? Okay. So now just think of this representation. I have changed the intercept value to beta 0. Okay, so let's consider the equation of this one. Remove this error for now because that is what we are trying to find through y cap minus y. So for y cap, it shall be beta 0 plus beta 1x, or just say beta 1x plus beta 0. Cool. That is the term we want to minimize with respect to because that is my slope. Okay. And for the intercept, I have another value beta 0. Okay. For intercept, I have the value beta 0. So we try to optimize this or to minimize this. And how is this done? Through a technique called gradient descent. Okay. To obtain the best fit line or to obtain the cost function or error representation, we try to minimize the value of the cost function to find the minimum error value, right? Now, consider this gradient descent graph. Okay, so from this cost function, we have calculated and all. Now, for this value, for this A basically represents your beta 0. Okay, and this is your cost function value, which is C. Okay, so on your y-axis, you have C, and your x-axis, you have beta 0, right? Okay, so this will result into a parabolic shaped structure where my minima lies in this valley. So this area considers negative slope and this area considers positive slope. And the value in the formula part to minimize the versus result, you have to take square on both sides, right? No. Why will you take square? This is your formula. C is equal to 1 by 2m summation over y minus y bread whole square. Okay. Good. Now we want to find the minimum value of what? Of this error. And what does that how does that depend on and what does that depend on? Do you remember that I said that once we truly estimate or we nearly estimate the values of M and C, I can predict the future values of what? I can predict the future values of Y. Right. So I need to estimate the value of M. Here basically what we are considering for beta 0 and beta 1. So I need to optimize this objective function with respect to beta 0 and with respect to beta 1. Interception point will remain the same. No, it might change. It might change. And that is why we are finding it for both beta 0 and beta 1 for a simple linear regression, because beta 0 is my intercept and beta 1 is my slope, right? Okay. Okay, for now, let's just, since we are talking about it verbally, let's just consider it to be of the form mx plus c, y is equal to mx plus c. So first we need to, and considering that now we want to optimize with respect to m. That means we are trying to estimate the value of m. Okay. So we need to partially derive this function c with respect to m. Then we get a curve like this, a parabola. On the left hand side of the parabola, I have the negative slope, and on the right hand side of the parabola, I have a positive slope. Cool. So suppose you start initially from this. We need to find a value that will reach the ball here. Let's consider this to be a ball, and we want the ball to reach at the global minima or the local minima. In this case, let's consider the global minima. Okay. So how is this done? This is done via m nu equals to m old minus some parameter alpha, or say eta, into del cost by del m. Okay. Did you understand, or should I try show a photo of it? Let's see. Just give me a few minutes. So are you able to see this image? Hello. Okay, zoom a bit. Uh-huh. It too much. Now, so I had the cost function c. Sorry. Mm-hmm. Clear? Is the image clear now? Okay. So I had the cost function c, which is 1 by 2n summation over I to m, I is equal to 0 to m, and y minus y bread whole square. Clear? So first I need to find the minimum m value. Okay, and with I want my cost to be the minimum with respect to the m value. For the m value, when I partially derive the cost function, I receive a parabola like this. Okay. I receive a parabola like this. So suppose initially my point, the value was at this point. Okay. I want it to be down in the valley. So I need to change the values so that I can reach the value. And how is that done? Using m is equal to m minus alpha into del cost by del m. And we repeat this until we receive the minimum value. Okay. So we start with the initial parameter guesses for n, and we update it step by step using this formula until we reach a value where there's no such change, right? Then we can say that the model has converged. Okay. Now you might be wondering, what is this alpha? This is the learning rate or positive constant. So what does this do? This this maintains or controls the rate of change of these balls. Okay, of these values. Okay, so if it is too high, then I might reach there directly to the value, or I might skip it to the positive part or to the negative part and eventually never reach the value, right? But if we keep a very small learning rate, then gradually I will go slowly to the valley, and then I will oscillate around it I ultimately till I reach the value or the minimum value. Okay, clear? So are we good with gradient descent now? Does anybody have any doubt? Yes, sir. Okay. Yeah. So we estimate the minimum m values, and thus we can further, once we obtain these values, we can fit the new data into these points and ultimately reach the predicted values for y. So did you understand the entire structure for linear regression? Okay, cool. What about the intercept? Then you need to also need to derive using the intercept. Okay. Next, I'll show you another image. Just wait to get the entire job done. Just give me a few minutes. I thought that I wouldn't require these images, but it seems like it is a good approach if I show these images to you. So is this image visible to you? Mhm. Just give me 2 minutes. Oh, okay, so now is it visible clearly? Just let me know once. You zoom a bit. Okay. Okay. So can you see it properly? Cool. Nice. Okay. So your data set will look like something the input matrix X. Okay. So you will have m data points, or that is m samples, each being n dash, each having n dash features. Okay. So now for the input data set X, I add an extra column, each containing one. Okay. So slowly we'll understand why I'm doing this, that I'm adding an extra column of one. Okay. And you have the y vector that is of m samples, and each sample will contain one element, which will basically be the label or the value for the corresponding value for these x features. Okay, for one sample I suppose this is a house price based video. It is a row vector, or you can consider it to be a this is a row vector. No, this is a column vector because I have only one column, m rows. Okay. Look, so you have a vector y having m samples, and each sample will have the final predicted value, not the predicted value, the original value of these corresponding to these samples. Okay. So suppose you have a house price data set, each vector element has row vector. Okay. Hmm. Each vector element has a row vector, you can say. Okay. So I have this vector y course where each element of that vector says that I have been derived originally for these features. For M, suppose it is a house price data set, you have certain features for the house, and then you will say that these features correspond to this price. Clear? You remember the equation for multiple linear regression, right? So you have it in this format, theta n dash x n dash till theta 0. Now why did I add this one is basically to obtain the value for theta 0. Okay, so my theta will be an n cross 1 vector. Okay, so that I can eventually receive y is equal to x theta. So y be x being the m cross n, and that being theta cross n cross 1, theta being n cross 1. So I ultimately receive my y cap of theta of m cross 1. Then I have the cost function y minus y cap whole square summed over y is equal to n. Here m is the number of samples as we saw from the dataset, and it was 1 by 2m, which is equivalent to 1 by 2m y minus x theta whole square. So this is a matrix multiplication, right? It is basically y cap. Now, if I need to obtain the minimum values for m, then basically I need to derivate or to derive this expression with respect to theta. Okay, so since we are considering theta matrix, by default you can say it will lead to a big summation expression, and then ultimately for each value of theta I will get the estimate for that theta value. So for theta 0 also, which is my intercept, I receive the value by default. Okay, so this is my dc by d theta, and I place it in that gradient descent value equation and receive my final value. Cool, understood? So this is the learning. You can say that this is the learning part of the linear regression algorithm. Is it clear, everyone? Do you guys have any doubt regarding any part we have studied till now? I'm ready to explain that again. Please let me know. Hello. It is y minus y cap, and y cap equals to x theta. So I have substituted the value of y cap to x theta. And this is why I've written in bracket. Basically, I'm emulating this here, right? In matrix form. Clear theta and its operations again. Theta is basically my slope. No, in the derivative. No, why is it y cap minus y? I'm telling you. So basically, when you are deriving y minus x theta with respect to theta, you will get what? 1 by 2m, 2 gets cancelled, 1 by m, y minus x theta into minus of x. Because y is a constant, so dy of d theta, this gets eliminated, and you have minus x minus dx of dx theta. So this minus sign gets in within these brackets, and you eventually get y cap minus y. Clear? So why we have divided by 2m, so that when we get the 2 by partial derivation, we can just cancel out the two terms to cancel it out, nothing else. No other reason to it. Clear? Any other doubts? Wait, think I have missed. Explain the column of ones. Okay, I'll explain it. Repeat what theta was. Okay, repeat what theta was. So theta parameters are basically the slope parameters. Okay, so just consider y is equal to mx plus c. Okay, so instead of writing it as slope, I am rewriting it as y is equal to theta 1 x plus theta 0. So theta 0 is my intercept and theta 1 is my slope. Cool. Explain the column of ones. Okay, so I'm additionally adding a column of ones so that when I am performing x into theta, I have a feature for theta 0. So basically the equation should be y is equal to x1 theta x1 plus theta x2 till theta xn plus theta 0, right? So how will I obtain theta 0? Okay, I need a 1 to it. I need it to have a 1 coefficient to it to multiply it to a 1. So this is why I'm adding an extra column of 1. Okay, I have too many text not in the narrative. Huh? Okay, okay, yeah. Can you give an example showing features? Wait, I'll explain. So you have any theoretical doubt? Next, we will do a from scratch coding, so you'll understand it fairly enough. Scroll down the image, please. There's nothing else in this image. So this is all about this image. So this was initially a rough work. And since I'm explaining it to you, I thought let's put it here as well while explaining. Clear? Does anybody have any doubt left? Then we can shift to the code. No doubt means we can shift to the code. Can you explain why interpret equation? Why interpret equation? This one. Why estimation equation? Okay. So basically, you are trying to fit a straight line that is done through y is equal to mx plus c. Okay, or y is equal to theta 1 x plus theta 0. Now for multiple features or for multiple x values, then we need to find the slope corresponding to those x values. So the equation turns into y is equal to theta 0 plus theta 1 x1 plus theta 2 x2 goes on till theta n xn. Clear? Uh, So no doubts remaining? Okay. I hope no doubts remaining. Cool. Third floor. Hmm. So let's see. So I have a data set, a custom data set called data.txt. Okay. Hey, do you remember the syntax technique for I used to follow for uh, those automaton those Python classes? Then I'll frame it according to that. It was this class. What was that collab notebook? Hmm. Linear regression. Hmm. Thank you. So I'll create a folder in my drive. I'll upload these codes there, these data there, and I'll upload the PPT to there. And I think should I upload the notes as well? Those two images. Then I can like combine them in a page. And okay, cool, cool. Please do upload the set. You can create the data set yourself. A very small data set. So I follow um, a website called a YouTube channel called Learn with Jai. Okay, called by someone named Jai Patel. He explains these codes very nicely, so you can learning from scratch. And when I was a student, I used to learn from that. I still am a student doing my master's. Okay, so I need to load the text. Here you can write the file path. So since they are in the same folder, I don't need to do any such hard work. I'll just write the whole file name delimiter equals to comma. Let's see how the data looks like. So it is an array of two columns where the first one is my area of the house in terms of say square feet, and this one is the price for it. Okay, clear? Next, let's we need to create my sample data set, that is being 0. Now I need to add into X a extra column of rows. So this is done using this vstack command function np dot ones. I hope you remember what np dot one does. So it is only of size x size. Then done. So, this work is x dot size. Yes. Hmm. So let's check the sizes for these, or rather the shape for this. Hmm. Use some syntax problem. Release the bracket open, np dot ones, np dot ones. Next. Hmm. Done. So we are done preparing the data. Let's see how this looks like. So this is how my points are distributed. Now we build the linear regression model. I need the input data, I need the input values. The Can you explain the code you have written? Each part. Okay. So basically, what this does is that I'm picking the zeroth column, I'm picking the first column, and I'm reshaping it with respect to the size of x. Okay. Then I am stacking into x a column of ones. Okay. So that is done using the np.ones. Okay. And this means that I will only add with respect to the x dot size, that is the number of samples in x. Okay, cool. And I'm transposing the entire matrix so that later on I have no problems with respect to x after and before modification. Okay, so why we add x in the first column? So that, see, my equation is of the form y is equal to theta 0 plus theta 1 x1 plus theta 2 x2 plus theta n xn. Okay, so later we need to multiply x theta to calculate the value of y pred. So y cap, which is my y pred, is equals to x into theta. I have, say, xn points. Okay, but I do not have the points for the sufficient number of points for theta. Okay, no, wrong way. For example, now if I have theta n minus 1 x values, okay, but I have n theta values from 0 to n. Let's consider n theta values. Okay, sorry, that will be n plus 1. Yeah, so I have n plus 1 theta values and I have n x values. So I need, so if I'm multiplying these two matrices x and theta, I would also require one of the parameters to act as a multiplier or as a coefficient for theta 0, right? So theta 0 can be considered as theta 0 into 1, right? So this is why I'm adding a column of 1 into x, so that when theta 0 gets multiplied to that 1, the theta 0 stays and is not vanished. Clear? So, so what was my aim? Number of samples, then theta is equal to, let's say I'm creating an empty matrix. So how many parameters we have? 2, 1. Like theta 0 and theta 1. These are the two parameters for now. Okay. You can obviously automate it later on if you are trying a multiple regression. This is easy. That would be your task rather, to complete multiple regression. It's very easy. You can just follow these along and let's see how does your creativity work. So this will basically contain the loss values. What was my loss? Basically the cost that I arrive into, the eventual cost that I arrive into. Okay. Hmm. So next I have this being my theta. and I'm formulating it into this. So I need these two values. I need basically the theta to find the estimates or the wipe rates. So basically, let's look into what has happened. Okay, so I have my initial y, then I have some theta which I am initializing at 0. So by doing this wipe rate equals to np dot x comma theta, I am drawing a wild line. Okay, so basically I'm randomly drawing a line. I don't care how does it look, from where it starts, whether it covers all the points or not, whether it covers even one point or not. I literally don't care. Okay, I just draw a line. Okay, then I find the cost for it, which is looks similar to the cost function that we have studied till now. Okay, and we go on changing it. How we need to calculate the derivative with respect to theta. There is del theta, that is the rate of change of theta. So that is done by the formula I arrive into is next. First, I hope how you arrived into this d theta. This was my dc by del c, sorry, del c by del theta equals to 1 by m into x transpose into y pred minus y, right? Is it clear what we are trying to do? Hmm. Okay. Okay. So by del theta, this d theta, I am trying to formulate del c by del theta equation, which was basically my by 1 by m into x transpose into y pred minus y. Clear? It is just that formula. Okay. Then I need to update the theta value. I need to update the theta value. Okay. So this process is basically gradient descent. Here, So far, so good. Are we on the same page? Now, we rotate these things or this, we rotate the line. The context is also what? Sorry. Hmm. So far, so good. Now, we do a certain number of rotations for this line. Let that be 100. Say 1 e. So then we calculate the theta cost list. So this part involves training the algorithm. Or maybe we can put it into main. Not a unit function. So let's declare something known as the main method. You know about this, right? This main method. So 1e minus 7 means 10 to the power minus 7. 0.00001. Will the learning rate change? No, you can obviously experiment for the different learning rate values, but for this, it will remain the same. Okay. For one program, it remains the same. Okay. We need to call the function, and by this, we have trained. So after this, mhm, but no to final result हो, ठीक है, बोल देगा तो बोल दिया है इंटरेक्शन आएगा तो mm-hmm. So we have uh, trained the value. Okay, so we have actually received a huge loss cost value. For this generally it's quite less, but here you have a very small data set, so obviously you will find such errors. So if I probably use for this and I skip this training for iteration number, Let's see if the loss value decreases. Okay, so it did decrease, but quite less. Hmm. Okay, so now let's estimate the test values. This is my test data. Mhm. Hmm. Okay. So thus we have predicted the final values. Cool. We are going to see for cost. Hmm. Value changes. Nice. Okay, so far, do you have any doubt? Okay, no doubts. Okay, so about today's class, uh, do you have any doubt? Do you have any remaining doubt? So I can just, plot this cost function select. Okay, so this is the loss for it. Uh, maybe I can train it for a fewer number of epochs, then receive a better card. Hmm. Okay, I haven't received the cost list. So this basically goes away. Hmm. I see the cost list here. So, okay, so this is what the loss loss convergence looks like. Cool. Explain the whole step-by-step process of this code shortly. Okay, I will. Himadri, what is house bracket 1? Okay, so this is basically the house. In house is one of these lists or one of these elements 1 comma 1547. Okay, so one row. By house 1, I mean 1547 only. Clear? Okay. So about the entire program, about the entire program. First, I have the data. Wait, let me all integrate all of these into the main method and provide you the step-by-step load the data. This is done using this. Okay. Then I need to prepare my input matrix. This is the prepare the input matrix. No, you won't get new house one. You'll get one. You have to write house one, house zero. Then you will get one. New house is one variable, right? From that you are picking one by house. Okay. So prepare the input matrix. Then you can see the data. I'm keeping this optional. You- so how to delete this cell? We can delete it somehow. We can now. Let's get first delete. Okay. Mm. So now, okay. So this is just my code. I'm controlling it to the main method, and I just need one function to um, do the regression part, right? Cool. Although not exactly relevant to this, but how do I increase the accuracy of a model? What step-by-step visualization? Okay, I'll check into that. Wait, first let me explain this. Hmm, okay, okay. So here it is, and then I call the model. In the model, what I do is first I have declared a variable for say number of sizes. Then I have checked for theta. I have created a sample theta, which is so that I can randomly plot a line. And this is my list for containing the loss values. Okay. Then for a certain number of iterations, I am just plotting a line. I'm finding the cost, and then I am minimizing the cost. Okay. Done. Then after the certain number of minimizations are done, I'm returning the theta and the cost value. Okay. Because I will need the theta to estimate my predictions. Okay. Future predictions rather. Then this part is done. Then I have used this to plot the convergence line. It is basically this loss versus epoch plot. Loss value versus epoch plot. Iteration is basically one epoch. One iteration is basically one epoch. Okay. Then I can print the last cost value that I have achieved. Then I use the testing. We'll look into the testing factors tomorrow, like accuracy and all. Okay. And then I have created a test data. Then I'll see what is the value I receive. Clear? Okay. Shinjan says all are exactly relevant to this, but how do I increase accuracy of a model? Example, seeing correlation to without redundant features. Yes, obviously you can do that. Okay, but apart from accuracy, you can also do feature extraction just to keep the relevant features, most relevant features. And while at the same time, from overfitting, we have to look at the bias variance trade-off. Okay. We can look into that tomorrow, vice variance data. And apart from that, you can train on a huge data set so that so how can we understand that the cost is minimum? I make a function for hit and trial starting at any random point. Yes, you start at a random point and then you just calculate it in a calculative manner, you decrease the value. And how can we understand that the cost is minimum? Let's say you can say that, oh, for avoiding overfitting, you can also the use the early stopping criteria method, which is if two loss values have a very minimal change, say do not change after the seventh or eighth decimal place, then you can say that the loss value on for almost two variables is just the same. So you keep it like that. Okay. There is no change required and you can stop. So early stopping criteria prevents overfitting in most of the cases. You can train on a huge data set to so that a better inference is drawn. Cool. And how to understand that the cost is minimum. See, when you already have hit this curve, okay, that is, then you can say that the loss can't decrease anymore. See, as you can see in this image, in the loss versus epoch plot or the cost versus iterations plot, that the values after a certain point, the cost values are constant. They do not change. You can't decrease them. Okay, it is just stagnant. So you can say that the model has converged. Okay, and that means that you have hit the cost value which is minimum. Cool. Any more doubts? Okay, so you have understood linear regression very clearly, right? You have covered it quite in depth, including the gradient descent part. Okay. Explain data test again. Data test means data set or data test or test data. Test data is a sample data that I have created on which I'll check the performance, how good is the model performing on data that it hasn't seen before. Okay, so the model has been trained on a separate data and this is a new occurrence to it. So we want to see whether it can predict properly or not. This is test data. Cool. Okay. Okay. So do you have any more doubts or I shall end today's class?